Imagine designing a building and then you click the Analyze button and suddenly your screen is filled with colored lines, numbers, and diagrams. For many engineering students and even some practicing engineers, this is the point where they become confused. They don't know what they are looking at. They simply wait for the software to tell them whether the design passes or it fails. But that is not how structural engineering works. Before checking reinforcements, an engineer must first understand the behavior of the structure. And that is exactly what the analytical model tells us. So today, I'm going to explain every major result in this analytical model using this actual building project. But let's begin with a simple question. What exactly is an analytical model? When you draw a beam in Protastructure, you are drawing a concrete. When you draw a column, you are drawing a reinforced concrete. When you draw a slab, you are drawing a physical building. But computers don't understand concrete. They understand mathematics. So before analysis begins, Protastructure converts your entire building into a mathematical model. Every beams, it becomes a line element. Every columns, it becomes another line element. Every slabs, it becomes shell element. Every beam columns intersection becomes a node where forces are transferred. So think of it like a Google map. A Google map doesn't see houses, trees, or traffic lights. It converts everything into roads, intersections, and coordinates so it can calculate the shortest route. Protastructure does exactly the same thing. It converts your building into a mathematical element so it can calculate how load transfer from the roof all the way down to the foundation. So let's look at the load part. One of the first things every engineer should understand is the load part. Imagine you are standing on the first floor. Your weight is transferred to the floor slab. The slab transfers that load to the beam. The beam transfers it to the column. The column transfers it to the foundation. Finally, the foundation transfers everything safely into the soil. That is called the load part. If the analytical model is incorrect, the load part becomes incorrect. And if the load part is incorrect, your design result cannot be trusted. So now, the display end diagram. The end diagram. The end diagram is stand for axial force. Axial force, and axial force is simply a force that is acting along the length of a structural member. So think about squeezing an empty plastic bottle from the top. The forces travel straight down. So that's compression. Now imagine pulling a rope. The forces also act along its strength. That is tension. So column mainly carry compression. When I display the axial force diagram, notice that the column have the interior columns, they have larger value than the edge column. So there's an interior column. There's an interior column. Now look at the edge columns. So the value, the compression value, they are much larger. They are much larger in the interior compared to the edge column. And why? This is because an interior column receives load from beams in multiple directions. While an edge column, they support fewer beams. So naturally, the interior columns carry more load. If I ever see one column carrying a force that is far larger than every other column, I will immediately investigate because it could indicate a modeling problem or an unusual heavy load. So now let's talk about the shear force. That is V2. This is the shear force. So now imagine you holding a deck of playing cards. If you push the top half sideways, the card begins to slide over one another. That is shear. Now imagine a simply supported beam carrying a heavy load. The highest shear force doesn't occur in the middle. It occurs near the support because that is where the reaction are resisting the applied load. So this explains something you see in construction drawing. And then why stirrups are closer together near the support, because that is exactly where shear is highest. So V3 is simply a shear that is acting in the second local direction. So for most buildings carrying gravity loads, these values are much smaller. They are much smaller than V2 because the beam mainly resists vertical loading. So large unexpected V3 values, they may indicate an unusual loading condition or that something in the model should be checked. So the next one is torsion. Torsion, it means twisting. So you can just imagine holding one end of a towel while twisting the other one. That is torsion. In building, torsion commonly occurs in edge beams supporting cantilever slab, curved beam, or structure with irregular layout. So in this project, the torsion values are relatively small, and that's a good sign because it suggests the load are being transferred without excessive twisting. Then we have M22. This is the most important result, and that is the bending moment. So imagine you placing a wooden plank across two blocks. When someone stands in the middle, the plank bend. That bending creates bending moment. So notice how the largest positive moment usually occur within the span, while negative moment develop over the support and continuous bend. So this moment determines where reinforcement is required. Bottom reinforcement, it resists positive moment. Top reinforcement, it resists negative moment. So without bending moment diagram, we wouldn't know where to place this steel. Then lastly, we have M33. M33 is bending about second local axis. Some beams show higher value because of their orientation within the building. That is why understanding local axis is also important. So two identical beams can display different moment diagrams simply because their local axes are different. So now, can we now say the building is safe? This is where many engineers make a mistake. They think that once the analytical model looks good, the building is automatically safe. That's not true. The analytical model only tells us how the structure behaves. It tells us, are the load flowing correctly? Are the beam behaving as expected? Are the column carrying realistic load? Is there excessive torsion? Is the overall structure behavior logical? So only after confirming some of these answers, that's when we can move to reinforcement design. That's where software checks whether every beam, slabs, and column is actually strong enough. So whenever you finish analyzing a building, don't rush straight to reinforcement design. Spend a few minutes studying the analytical model. Ask yourself, do these forces making engineering sense? Are the heavily loaded column where I expected them to be? Are the beam moments reasonable? Is the torsion acceptable? The software perform the calculation, but it is your engineering judgment that turns those calculations into a safe structure. And that is what makes the difference between someone who knows how to use Protastructure and someone who truly understands structural engineering. Thank you so much. If this video helped you understand the analytical model, let me know in the comments which result you want me to explain next. The beam design, or the slab design, or column design, or even load combination. Subscribe for more practical Protastructure tutorial, Euro code design tips, and real engineering projects. I will see you in the next video. Thank you.